Okay. All right, so I'm going to introduce the speaker. Kun Yang obtained his PhD from Indiana University in 1994. He did postdoctoral work at Princeton and was a Fairchild Research Fellow at Caltech before joining the faculty of Florida State, where he has been ever since. He does elegant and important work on strongly correlated matter, including bilayer quantum Hall systems, graphene, random magnets, and over the past few years, the body of work that he's going to tell us about today. Kun is also the author with Steve Gerwin of a magnificent new textbook, Modern Condensed Matter Physics. And for the people who are in the room, you can see it and heft it if you like. There are many fine books on the subject. The way in which Gerwin and Yang is different is that it's not only a book for students, but also a book for professors.
And ourselves, authors too, as a matter of fact.
Also for students, yes, it's for students and professors. As the blurb at the back says by Subir Sachdev, it's highly recommended to all physics students, to researchers seeking to reset their foundations. And I think there's a saying that you should make everything as simple as possible, but not more. And this seems to be the guiding philosophy of their book. Kun told me that this book was a huge labor. So I'd like to assure him that it's very much appreciated by the community. And I'm looking forward to learning from it and teaching from it. So with that, welcome. The floor is yours.
Well,
okay, sure. I think we'll probably just be working right here.
Yeah. No, these are pointers that will work with that screen, but we don't need to mention it.
Well, we'll see if it works here. We'll stick, but otherwise we can switch. Well, thank you very much, Harsh, for the kind invitation. This is actually my first business trip and actually first in-person seminar since the pandemic hit. I guess it applies to all of us that we have heard many Zoom talks and given a number of them. I have actually given several Zoom talks, both seminars and conferences. I think scientifically they mostly work well. But one thing that I don't like about Zoom talks is that the jokes don't work quite as well. So one thing I'm very eager to actually find out today is whether my jokes still work. So you guys tell me afterwards. So anyway, so the title of my talk today is Interplay of Topology and Geometry in Fractional Quantum Hall liquids, which of course contains a number of buzzwords, which I'll try to explain. But in the spirit of making things as simple as possible, and I was told that there may even be undergraduate students in the audience. So let's actually go all the way to the back to the Hall effect. Okay, so why is this not flipping? So never happened before. Huh, screen froze. Restart this slideshow. No, it's flipping. Okay, so let me start actually all the way back to, I guess, maybe high school physics, maybe even further back, which is what is Hall effect? Well, this of course is when you pass current through a conductor. So let me see, can people see the pointer? Well, I guess it's showing us on the screen, so I suppose it's visible for Zoom audience as well. Well, in addition to the longitudinal voltage that actually maintains the current, when you have a magnetic field, there's also additional so-called Hall voltage that is actually perpendicular to both the magnetic field and the direction of the current. And obviously, the origin of this Hall effect can be understood in Newtonian classical mechanics, basically because the current flow is, let me see if I want to do, well, okay, this is visible again now. The current flow is due to electron motion, and the moving electron experiences a Lorentz force due to the magnetic field, which tends to bend the current. And that actually induces accumulated charge on the two sides of the sample, which actually gives up to the Hall voltage until the electric field associated with the Hall voltage balances the Lorentz force. So let me see if it works better if I do the, okay. Yeah, I don't have, well, yeah. Okay, well, the pointer, I guess this is my mouse.
You want to make a pointer?
If it actually, yeah.
Lasers don't usually work on screen.
Yeah,
but
yeah.
you can convert, if that's PowerPoint, you can right click and call up a red.
Yeah, let me try to actually do a pointer option, which actually, yeah. Okay, yeah, I think this is probably better. Yeah.
Yeah, you can also hide the
Get down to more, right?
Get down to more.
It's gone already.
It's gone.
Oh, it's gone. Yeah. Okay. Thank you. Yeah. Thank you. Yeah. Okay. So I think.
The point is gone.
Oh, the point is, well, okay. Anyway, I'll stick to this. Okay. So the point I'm trying to make is that once the Hall field or Hall voltage balances that of the balances the effect of the Lorentz force, then there is actually no effect anymore. So you can easily determine the Hall voltage, and actually that is always proportional to the current density. And you find that the Hall resistance, which is the ratio between the Hall electric field and the current density, is proportional to the magnetic field. Okay, so why is this happening?
I think if you go to more, you can. There's an option to hide the bar.
Go to more. So let me see.
Right next to leave.
Yeah, but I don't see it on my screen. That's the problem.
Unless it's on this screen.
Yeah.
Do I dare touch it and find out?
Go ahead. It's gone again.
Yeah, it's gone again. Okay. Well.
Okay. All right. Let's keep going.
Let's keep going. Okay. So the Hall voltage is proportional to the magnetic field. But what's really nice about the Hall effect is that the coefficient depends only on the density of the carriers, but nothing else. So therefore, it's a very useful way to actually determine or measure the carrier density. Now, another thing that is perhaps not quite as widely appreciated is that it's actually sensitive to the sign of the charge of the carrier. So it's sensitive to the sign of E. As a result, it distinguishes between particle carriers and Hall carriers. And therefore, it can tell you whether the system has electrons or holes as its carriers. On the other hand, as I said, as far as the longitudinal transport is concerned, the effect of the Hall voltage or Hall field cancels that of the Lorentz force, and as a result, the longitudinal resistance classically should be independent of the magnetic field. And of course, I wouldn't be giving a talk on quantum Hall effect, which this talk is about, if this is the whole story. And obviously, quantum mechanics changes things dramatically. So this is a very famous plot, and I wouldn't be surprised that some of you have seen this many, many times. I certainly have seen this probably more than 1,000 times in my career already. So this is the transport plot of a very high quality two-dimensional electron gas system, which is very actually, well, standard job for experimentalists to grow these days. I'm not going to get into a discussion of how to make them, which is the magnetic field dependence of both the longitudinal resistance, which I guess are these oscillating curves, and the Hall resistance. Now, at relatively low field, you do see the standard linear dependence with the coefficient telling you the carrier density. However, as you go to high field, which actually is not that high by today's standard, beyond several Tesla, but all the way to 30 Tesla, which I think you still have to go to the mag lab to actually attain that field, you see a whole sequence of plateaus on which the Hall resistance actually takes a quantized value, which is h over e squared, which is a quantum resistance, divided by a number called filling factor. And the filling factor are integers on these so-called integer quantum Hall plateaus, and fractional numbers represented in particular by the 1/3 plateau on these so-called fractional quantum Hall plateaus. And while the Hall resistance is on one of these plateaus, the longitudinal resistance, very importantly, goes to 0. Well, it's not exactly 0 at any finite temperature, but typically it goes to 0 exponentially as temperature goes down. So that's very different from the classical behavior that I was just explaining one slide ago, where you expect no dependence of the longitudinal resistance on field, while the ordinary Hall resistance is a linear function which only works here at low field. So
can I ask a question?
Yeah, sure.
It's really a tangent though.
Yeah.
I remember when we were in grad school, people used to ask this question. They used to say that the lower curve is the derivative of the upper one. And people used to try to explain why that is true.
I don't think that's exactly true though. I mean, empirically, I think in the early samples, which are dirtier, there seems to be a empirical observation, and I think there were theories for that.
Right.
Well, maybe more phenomenological than fundamental theories for that. But I don't think in general there is such a simple relation.
Okay, it's gone away now.
Yeah. I don't think it's discussed. I mean, I'm aware of that discussion, but I don't think that's still considered an issue.
Okay. Great.
Yeah, either. Okay, so it's actually quite remarkable that this one plot, if you wish, actually, I think this is data from a single sample, actually, well, not directly, but actually contains, if not directly, little, but actually contains two separate Nobel Prizes, one for these integer states and one for the fractional states, in particular, the 1/3 one. So I'm of course referring to first the 1985 Nobel Prize in Physics, which was awarded to von Klitzing, who discovered the integer quantum Hall effect in 1980. So that's a relatively short period. Then there's, of course, the 1998 Nobel Prize, which were shared by Horst Stormer and Dan Sui, who were at the Bell Labs at the time and did their experimental works that discovered the fractional sequence. And Bob Laughlin, who was also a Bell Lab postdoc, who also came up with the first theory of the integer quantum Hall effect, but more importantly, later on in Livermore, wrote down a very remarkable wave function, which I'm going to say a few more words on later on, that basically captured the most important ingredients of the fractional quantum Hall effect. And the three of them shared the 1998 Nobel Prize. So for a condensed matter seminar like this one, you actually start to wonder what there is to be talked about. I guess some 30 or, well, not quite 30, but 20 plus years. Well, over 30 for the first, but plus 20, plus 20 plus some years of the second Nobel Prize. Well, but the situation is actually even worse than that. In my mind, there are two more Nobel Prizes that are actually directly related to quantum Hall effect. The third one is a 2010 Nobel Prize for the discovery of graphene as a system that actually supports Dirac electron behavior. But the way they actually figured out we have Dirac instead of Schrodinger equation, Schrodinger electrons is this unusual sequence of integer quantum Hall states, which in some sense, not in the literal sense, but in some sense is actually quantized not at integer, but half integer values. And this, of course, is directly related to the fact that Dirac electrons has this pi Berry phase, which plays a role that's similar to half a plus quantum. But actually, this is still an integer sequence because you have not one, but actually four degenerate Dirac electrons, two associated with the electron spin and two associated with the valley degeneracy. So if you use 4e squared as over h as the appropriate unit of the Hall conductance, then you find that the quantization is not at integer values, but instead at half integer values. And that, of course, is a very direct manifestation of the Dirac nature of the electrons in graphene. And the Nobel Prize was awarded to the Manchester group people, Knobloch and Geim, but the Columbia group headed by Philip King actually made the same observation at essentially the same time. So the final one, or the fourth one, actually is the, now I see this on my screen, but not on the big screen, but never mind, is actually the most recent Nobel Prize for condensed matter. That's the 2016 Nobel Prize. And in particular, I'm highlighting the contribution of David Fowler, who actually, for the first time, pointed out that the origin of this quantization is actually topology. So this, of course, is actually a plot I copied from the Nobel Foundation at the time of the announcement of the 26th Nobel Prize. So basically, if you work in a bakery, you can make all kinds of funny stuff with different number of holes. Okay, so this looks like a pretzel, but you can also make a cup out of your flowers. But when you actually continuously distort the shape of your material, if you wish, the topology, namely the number of holes, does not change. So therefore, there is a stability associated with that. And the quantization of Hall conductance is in some sense for the same origin, namely the quantized value of the Hall conductance is a direct measure of this topological quantum number, namely the number of holes here. So since then, this has been more and more widely appreciated, and I'm sure you have heard a lot about topological physics, especially in condensed matter seminars. But now it is actually a notion, namely the notion of topological phase and topological order, which are actually widely used in all branches of physics. So today's talk, on the other hand, is actually in some sense moving in a orthogonal direction. So I did have topology in the title of my talk, but this is actually not the aspect of quantum physics I'm going to actually emphasize. Instead, I'm actually going to emphasize a different aspect, namely non-universal physics. So the topology gives rise to the quantization, which is the universal aspect of the physics. But as I'm going to explain, there's actually very interesting non-universal physics in these fractional quantum Hall liquids. And as Helen pointed out in a paper very important to me a very important paper almost exactly 10 years ago, some of these non-universal physics is actually associated with geometry, not just topology, although topology does actually also play a role in it. And the first specific result I'm going to report today is that this topology not only exists, it actually can be measured fairly directly experimentally, and indeed it has been measured. And the theory has matured to a degree that actually allows for a quantitative comparison between a theory and experiment. This geometry or geometrical degree of freedom not only exists, it actually has very interesting and highly non-trivial quantum dynamics. And Haldane and also Song and their collaborators pointed out their quantum fluctuation or their quantum dynamics gives rise to a spin 2 excitation, which I'm going to call for this talk gravitons. Okay, and I'm going to explain what's the physical picture for these gravitons. And the second set of specific results I'm going to report is that these gravitons can actually be excited and probed in various ways. One of the ways which actually haven't been realized experimentally yet is to use acoustic waves, which I'm going to argue behaves very much like gravitational waves. So it's kind of natural that you can actually excite gravitons using gravitational waves. And perhaps more importantly, these gravitons have a very specific chirality. So they're chiral, okay? And the chirality can be revealed using a different kind of probes, namely polarized Raman skeleton. And this is actually an experimental probe that already exists and have been actually used before to study excitations in fractional quantum Hall liquids. I'm going to actually make some comparison with existing experimental data, but the chiral nature of these gravitons haven't been revealed yet because the previous experiments were not using polarized light. The chirality we claim for the laughing state that I talked about a little bit is known. And this actually is prediction that can be tested. But more importantly, we can actually apply the same method to study another very interesting quantum Hall state at Free factor 5 halves, whose nature we actually don't know yet. And therefore, this experiment, which I hope will be performed in the near future, can at least help and has the potential of revealing the true nature of this very interesting new state. Well, not that new anymore, but new in the sense that we don't know what's the nature of that state. Okay?
So I have a quick question,
yes.
Although it might be something you will address right away. So I thought that the elementary neutral excitations were these magnetophonons and magnetorotrons.
Magnetorotrons, exactly.
Yeah, so are these the same thing that are being reinterpreted, or are they
right.
new excitations?
So maybe you can actually make the judgment after I present my results.
Okay.
So it's actually closely related to magnetorotrons.
Mm-hmm.
Now the magnetorotrons were best understood at finite wave vector, but these gravitons are actually long wavelength excitations that are actually in the zero momentum limit. So the relation between these finite wave vector magnetorotrons and the long wavelength excitation, I don't think we're completely understood, but I think now we understand their relation, which is something that I'm going to explain. Yeah. Okay. But before, of course, going into these, if you wish, more sophisticated, maybe in quotation mark results, let's actually understand something basic, which is the origin of these plateaus. So, well, I guess in retrospect, the integer plateaus, as represented by the new code 1 plateau, is in some sense rather trivial to understand, in the sense that you don't need to invoke electron-electron interaction. You perhaps don't even need to have a full quantum mechanical description, but instead using some kind of semi-classical picture, you can actually understand it. So we all know when you
plateau at 2.
So there is a plateau at 2 as well, but the plateau at 1 is the simplest. But
from the picture, there doesn't look like there's any plateau.
There is one. Yeah, this is a 2. Yeah. Well, I mean, it's not quite as wide. So part of the reason it's not quite as strong is because the magnetic field is weaker.
And RH equals 2?
No, RH, okay, so sorry. These numbers are in the denominator.
Okay.
Yeah, so the quantized value is written as for the whole resistance is H over E squared divided by the field effect. Now, another way to plot it, which may be better, but that's not how experimentalists do it, is to plot the whole conductance. The whole conductance would be E squared of H multiplied by, for the integer sequence, an integer. So then you will get 2 in the numerator instead of the denominator. Yeah, I realize that's a little confusing, but here the integer is in the denominator. Yeah. Okay. Okay. So as it turns out, and I'm going to explain, you can, well, in retrospect, understand the integer quantum force state by actually using some semi-classical description of electron motion in the magnetic field. So we all know, of course, when you put charged particles in a magnetic field and set it in motion, what you get is a cyclotron motion. So these electrons are basically just running around circles. So they're actually not going anywhere. And as a result, they actually don't directly contribute to transport. Well, then it looks like the system should be insulated, but that's not the case. We actually do have quantized Hall transport. Where does that come from? Well, that actually comes from the electrons that live near the boundary. So let me see if I, yeah, okay. So let's say if I stay at the right boundary, you find that these electrons are also trying to actually exit. Well, okay, so yes, I'm proud of myself. Still better to, yeah, don't have my mouse with me. So yeah, anyway, so if you look at the trajectories on the right side of the plot, you find that while the electrons are actually trying to complete a cyclotron orbit, before it can do that, it actually bounces into the wall and it actually bounces back. But once it bounces back, it continues. It's well, with a different initial condition of initial condition, try to actually start its cyclotron motion again, but then keeps bouncing into the wall. But while doing that, it's actually drifting from up to down. Okay, and the electrons on the left side is doing the opposite. It's also trying to do its counterclockwise cyclotron motion, but again, it's actually bouncing into the wall. But this kind of bounce or skip the cyclotron orbits actually takes it from down to up. So as a result, these electrons can actually move from one end of the sample to actually the other end of the sample. And it's actually these so-called chiral edge states that is actually responsible for the dissipationless and quantized Hall transport. So why is it dissipationless? It's dissipationless because the electrons on the right can only move downward. Of course, dissipation of resistance occurs when you have backscattering. But in order to backscatter these electrons, you have to take them all the way to the left-hand side. But these two channels or these two edges are separated by millimeters, which is the typical size of the samples. So that's actually impossible or negligible, at least at low temperature. And as a result of that, the transport due to these chiral states turns out to be dissipationless. Well, why are they quantized? Well, that actually is where quantum mechanics, well, not full-fledged quantum mechanics, but semi-classical quantization rule comes in. So the number of these states is actually limited because the size of these orbitals is actually quantized. So we know that, let's say in the lowest lambda level, this orbital has to enclose exactly 1 plus quantum. So therefore, the number of states that's available to the electron occupying, let's say, the lowest lambda level is actually determined by the magnetic field, actually the commensuration between the magnetic field and the flux quantum. And that actually in turn limits the current carrying ability of these chiral states. So that's actually a well, somewhat hand-waving and a semi-classical way to understand this integer plateau, the simplest one perhaps. So here comes my first joke, which I'm not sure is going to work. So well, I don't know if there are students in the live audience, but I suppose there are students over the Zoom. Well, when you're taking courses, well, I mean, you're like these electrons. These electrons in the bulk. Well, I'm sure you are getting good grades, so it's like smooth sailing. So everything is actually just going fine. But you may be running around circles without realizing. But once you start doing research, it's like these electrons. Well, samples may break, apparatus may fail, your papers may get rejected. But if you keep going, eventually it gets somewhere. So the lesson here is that don't give up. Even if you run into a wall, just keep going, and you can go from one end to the other and accomplish your goal. Obviously, this joke didn't work that well, but that's my best attempt. Anyway, so one pictorial way to actually characterize this kind of motion is using so-called dancing patterns that I think is a term that Xiaogang Wang first introduced. So the dancing pattern for these integer quantum Hall states is actually very simple. Basically, every dancer just does her individual dancing with two rules that needs to be followed. One is a quantization rule, namely this size of the loop or the step size is quantized. Okay, so that's one body piece of physics. The other, of course, is the Pauli principle, because electrons are fermions, and as a result, these dancers have to stay in her own territory, and you should not step into your neighbor's territory. So basically, following these two rules, you can actually understand, or at least pictorially describe, the basic physics behind integer quantum Hall effect. But the fractional quantum Hall effect, as represented by this, let's say, 1/3 plateau, is much more interesting. Okay, so I'm now going to try to explain the dancing patterns or dancing rules associated with the fractional quantum Hall state. So here, because of the lower filling factor, meaning you have fewer electrons for the same field, you have more room for dancing. So instead of sticking to your own territory, you're now allowed to dance around. However, because of not just the Pauli principle, but mainly because of the repulsive Coulomb interaction between electrons, you want to stay away from the other dancers. And the rule you need to actually follow is that when you approach another dancer, let's see, so yeah, again, okay. This guy, let's say, is approaching this guy, with this lady maybe, you need to actually loop around the other dancer. And again, you have a 3-step rule. Namely, the loop that you dance around this existing dancer has to enclose exactly 3 flux quanta. So this actually gives rise to some very unusual properties. So you might have noticed, but I forgot to emphasize that in the quote or in the citation for the Nobel Prize, the main justification was that this 1/3 liquid is highly unusual in that it actually supports fractionalized excitations. And what that means is that the elementary excitations, unlike the integer states, are not electrons, but actually in this case, in this particular case, a 1/3 charged quasi-particle. Well, how can you even understand that possibility? Well, let's actually assume the following situation, that you have a whole bunch of dancers on your dancing floor, your ballroom, and there is a big pillar here. And obviously you don't want to bounce into this pillar. So therefore, as the electron or your dancer approaches this pillar, you have to actually dance around it, okay? Now, because of the quantization rule, the one-body quantization rule, this loop, the smallest loop that you can have, has to enclose one flux quantum. Now let's actually compare the situation with that of an electron. So when you have an electron here, the other dancers have to actually stay 3 steps away from it, or actually the loop around it, the existing dancer has to enclose 3 flux quantum. So therefore we find that the area ratio between this pillar and that of the electron is 3:1. Now obviously, because of the existence of this pillar, some charge is depleted from it, right? Because all the electrons are trying to stay away from it. So this, this actually allows you to easily determine how much charge is depleted around this pillar. And that's 1/3 electron, because the electron occupies 3 flux quanta, but this one, because of the one-body quantization, has to actually enclose 1 flux quanta. So that's one way to understand why you can have fractionally charged quasi-particles. Basically, this is like a topological defect in your dancing pattern, okay? Anyway, so another way to actually represent this dancing pattern is precisely the picture on the cover of our book. I really appreciate how she's bringing a coffee here. So another way to actually understand the laughing pattern is to actually pretend that this 1:3 ratio, that is number of electrons and the number of flux quanta, is encoded or actually organized in such a way that the 3 flux quanta are all lumped onto individual electrons. Now, when you do that, the electrons are turned into the so-called composite bosons, because it's a composite object made of electron and flux. And such an object, of course, gives rise to a barrier phase when you actually have have them actually circulate around each other. And the barrier phase turns out, because of the fact that you have 3 flux quanta, you have actually an additional minus sign. And that minus sign actually cancels the minus sign due to the the Fermi statistics of the electrons. And as a result, the composite object is actually a boson. And the boson condense, and the condensation of the boson actually gives rise to the fractional quantum Hall effect. And of course, one could easily devote a full hour explaining the physics, but here I'm just making that analogy and claiming that this picture, in some sense, is a different way to actually encode the same physics of this picture on the lower right. Okay, so everything that I'm talking about here is actually topology, and we can have even more interesting topology, so-called topological order, as described by more exotic dancing patterns. So we talk about the trivial or integer dancing pattern and the laughing dancing pattern. And a frontier of quantum Hall research these days is the so-called non-abelian quantum Hall states. And the 5-half states that I mentioned early on is actually a candidate for that. And one possible dancing pattern is the so-called Moore-Reed dancing pattern. So in this dancing pattern, you actually allow 2 dancers to get as close as that is allowed by Pauli exclusion principle, okay? However, when the 2 of these electrons are close together and doing their intimate things, a 3rd electron or 3rd dancer have to actually stay away from this couple. And more specifically, in the Moore-Reed case, you need to stay 4 steps away, okay? So I really like this dancing pattern because it not only gives rise to this fascinating physics that we are studying, but it's actually very good for the social stability. Well, this is my second joke, which again didn't work as well as I was hoping. Anyway, so I'm going to talk.
Wearing masks, you can't.
Anyway, well, thank you. Anyway, so again, these are encoding the so-called topological order, and this last dancing pattern. Let me just finish this. Gives rise to not only fractionally charged quasiparticles, which, like the laughing quasiparticles, obey fractional statistics, but these fractional statistics actually turned out to be non-abelian in a way that can be used for topological quantum computation, blah, 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 which I don't think I will have time to get into. Yeah, please.
Yeah, so what's the pairing mechanism for the movie state?
Yeah, so turns out, okay, so one question is that you can actually describe these states using gauge theories, and gauge fluctuations is a possible source of the pairing. However, I think a more honest answer is, first of all, we don't really know. First of all, we don't even know if this is the case or not. But if you look at the Hamiltonian, as it turns out, so this actually happens in the first excited lambda level. So somehow when you project the Coulomb interaction onto the first excited lambda level instead of the lowest lambda level, it actually has automatically gives you a short range attraction. That has to do with the lambda level form factor, which I'm actually going to say a few words about later. Yeah, but if you want to ask me that question again. But in the more formal theories, you can actually write down some gauge theories, and there are gauge bosons which can play the role of the groups. Yeah. Okay, so everything that I'm talking about so far, which actually has been more than half the time that I'm supposed to use, is about the topological aspects. What about geometry? Well, turns out, well, as Haldane pointed out, this dancing pattern is not completely rigid. You can actually, for example, pictorially, of course, distort this loop, let's say from a full circle to a let's say an ellipse. But as long as this ellipse still encloses exactly, let's say, 3 flux quanta for the laughing state, the dancing pattern is still self-consistent. So this kind of a geometric distortion without changing the area is called area preserving diffeomorphism. So this was the main point, one of the main points of Haldane's 2011 paper. And based on this observation, he argues that there are both topological and geometrical aspects of fractional quantum Hall effect. And the latter is actually determined by energetics. So you might ask why you want to actually distort the dancing pattern this way. Well, obviously, as I said, the 3-step rule is to lower Coulomb interaction energy. But in an anisotropic system, let's say you have a anisotropic dielectric function that makes the Coulomb interaction, let's say, stronger in one direction than the other, then you might want to actually stay away from each other in one direction than the other direction. So then this dancing pattern may be energetically more favorable. Now, more relevant to what I'm going to talk about later, you could have actually effective mass anisotropy, which is quite typical in crystals. And then the natural dancing steps, if you wish, are already distorted at the one-body level. And that could favor this kind of pattern as well. And this is actually very important to what I'm going to talk about when I get to the specific results. Okay, so as a consequence of this, immediate consequence of this observation, we immediately realize that unlike what you have been told maybe many, many times, that laughing wave function is such a unique wave function that has no variational parameter. It's a variational wave function without a variational parameter. There is actually a hidden variational parameter which actually describes the geometry or anisotropy of this correlation Hall. So we have actually constructed a whole family of laughing states with the original laughing wave function being a very special member of, namely the one that is completely isotropic. Well, you can easily distort it to a different member of the same family, which obviously has a distorted and anisotropic correlation Hall, but with exactly the same area. However, because of the fact that the quantized Hall conductance is only sensitive to the topological aspect, the difference, let's say, between this state and this state is not manifested in the Hall transport. So just by looking at the Hall conductance and the fact that the longitudinal resistance goes to 0 does not distinguish between these states. So the question then is, how do we actually experimentally tell that there is this geometrical parameter, and how can you actually measure it? So it looks like topology gets in the way of actually seeing the geometrical aspect. But it turns out this question. Sorry.
Go ahead. So if it's really area preserving diffeomorphisms, wouldn't there be an infinite number of parameters?
Exactly. Well, so there should be a two-parameter family. So basically, you need to write down a symmetric 2x2 matrix. I mean, basically, that's going to be a metric tensor for you. But the area preserving diffeomorphism tells you that the determinant of the metric has to be 1. So you should have two independent ones. But one of them is orientation, the other is anisotropy. So the one that I'm plotting here, is actually the anisotropy, but I'm actually not specifying the orientation. Yeah. Does that answer your question?
Well, so that the diffeomorphism would, I could talk about moving the things relative to each other.
Okay, so diffeomorphism here means distortion.
Okay.
Yeah. So it's characterized by a metric tensor, which is a 2x2 symmetric matrix in 2 dimensions. So altogether, this should be 3.
So it's a diffeomorphism that's preserving the point.
Removes 1, so you're left with 2. So you can parameterize these to 1 by orientation, the other by anisotropy. Yeah. Patrick, you have a question?
I think maybe that's mine for the end.
Okay, yeah.
Or we might answer it on the way.
Hopefully, yeah. We'll see. So so topology gets in the way of observing this geometrical parameter, because all what you see here on the plateaus are just quantized value, which is not sensitive to this geometrical aspect. However, one state that is actually also of very high interest along this plot is actually this 1/2 state, which is actually not a quantum Hall state. Now, I'm going to say a few more words about the 1/2 physics, but here I'm just saying that in certain school of thinking, which I'm not 100% sure I'm one of them, you can view the 1/2 state as the parent state of all of these neighboring quantum Hall states. Well, maybe I would actually look at it in the opposite way, which is if you follow the sequence known as the Jane sequence, it actually ends at this 1/2 state, which is actually not a quantum Hall state. So if you assume all of these quantum Hall states have this geometrical aspect, then so should this 1/2 state. But the advantage of this 1/2 state is because it's not quantized, it's not protected by topology, you may be able to probe it, and that will tell you something about the geometry. And that, as I'm going to explain, is indeed the case. So let's actually take a look at the 1/2 state. And that's why I'm actually showing the cover of our book, in addition, of course, for the obvious motivation of trying to advertise it. So the difference between the 1/2 state and 1/3 state, of course, is the ratio. One is a 1:3 ratio, and the other is 1:2 ratio. Then by the same token, one way to understand or describe the 1/2 state is to pretend that the 2 flux quanta associated with each electron is all attached to the electrons, and then they form a composite object. But the difference here is that this composite object is still a fermion, because with 2 flux quanta, the barrier phase associated with the exchange is actually 2 pi. So therefore, as a result, it does not change the statistics. So when you have composite fermions, they cannot condense. And that's why they do not form a quantum Hall state. However, we all know what fermions want to do. They want to form a Fermi C. And indeed, starting from the early 90s, but still continuing today, there's a lot of interest and a lot of work devoted to actually understand the 1/2 state in terms of so-called composite fermions, okay? So one thing that we do know from early works is that yes, indeed, they form a Fermi sea, or they are associated Fermi surface. But one thing that caught interest only relatively recently is how is the shape of the Fermi surface related to the effective mass tensor of the bare electrons. More specifically, Shagan's group at Princeton has been asking this question, namely, if I have a circular or isotropic Fermi surface for electrons, that naturally leads to an isotropic Fermi surface for the composite fermion, and that has been well established from Shagan's work and also Bob Willis' work and many other groups' work. But they are asking a different question or a related question, which is, what if your original electron Fermi surface is actually anisotropic, but actually, for example, an ellipse? Without the symmetry, you wouldn't expect the composite fermion Fermi surface to be circular anymore. And first of all, you want to see if that's the case, and B, how you relate these two anisotropies. So yeah.
Presumably it'll get washed out, right? Because of the interactions.
Well, but not completely. So that's in some sense the punchline. It's washed out a little bit, but in some sense, the fact it's washed out by itself is actually already surprising. As I'm going to explain. Yeah. So let me actually not go into the details of how they do these experiments. It's a very standard procedure now, but just want to highlight one thing, which is that the way you encode this anisotropy of electrons is through this rank 2 tensor, which is the effective mass tensor, which I'm going to call a metric. Okay, and for reasons that's going to become clear. Okay, and you probably anticipated that a little bit already. So their finding is that yes, as expected, you have less anisotropy. Okay, but from the original school of thinking of composite fermion, that's actually a surprise, because if you just do the standard mean field theory, you actually smear out the flux carried by the composite fermions to cancel the external magnetic field. Then these composite fermions at that level would have exactly the same effective mass tensor as original electrons. And that would tell you or mislead you to think they should have exactly the same anisotropy. And people have indeed written papers making that direction, that prediction, which turned out not to be the case as Harsh actually anticipated. But that's, of course, a qualitative result, but the quantitative relation between them wasn't clear. So the first specific result I'm going to report will not only actually quantitatively give a quantitative understanding of the relation between the anisotropy, but perhaps more importantly, I'm going to argue that this composite fermion Fermi surface has a shape that actually directly reflects Condensed geometry. And the way that I'm going to establish that is through a exactly soluble model I'm going to present on the next slide. But here, I just, as a retrospect, point out there's something very similar, where at least for some of us very familiar in condensed matter physics, which also is area preserving diffeomorphism, but we didn't use that term, and that is known as Luttinger theorem. So Luttinger theorem says that you can change the shape of a Fermi surface, but its volume cannot change. So that therefore is also an area preserving diffeomorphism. Now, you might be surprised. Well, here we are talking about geometry from the surface shape in momentum space. But in the previous slide, I'm talking about geometry in real space. How can you actually relate these two? Well, turns out in the magnetic field, in some sense, real space and momentum space are actually due to each other. In particular, if you use the Landau gauge, you know that the momentum in one direction tells you the position in the perpendicular direction. So the dual relation between them is that the momentum space shape is a 90-degree rotated version of the real space shape. And all these are borne out in this exactly soluble model. Okay, so let's actually try to, so this is actually my only technical slide, which unfortunately I'm actually already coming to close to the end of the hour. So let's actually try to set up a general problem we can try to solve, describing many electrons in the lowest lambda level, or in a particular lambda level. It doesn't have to be the lowest one. So the lowest lambda level projection, the lowest lambda level approximation allows you to actually forget about kinetic energy. So in general, quantum mechanics is hard because we have kinetic energy and potential energy, but they don't commute with each other. You say, okay, well, if your professor, quantum mechanics professor, gives me a problem that only has the potential energy term, but not the kinetic energy term, wow, that should be the easiest problem I could encounter. Well, obviously, there's no free lunch. The problem, of course, is that you still have to project this interaction term into a given lambda level, usually the lowest lambda level. And when you project the position operator, which of course is what enters the potential term into the lowest lambda level, they become the so-called guiding center position operators. And these guiding center operators actually do not commute with each other. So this is actually still a highly non-trivial problem, which many of us devote many years of our career trying to tackle, of course, at this level in general. Now, what about the lambda level information? So how do you tell the difference between, let's say, the first lambda level and the second lambda level, or lowest and the excited lambda level? That's encoded in the so-called lambda level form factor. And the simplest one is the lowest lambda level form factor, which is the pure Gaussian, reflecting the fact that you have Gaussian wave functions in the lowest lambda level because these are harmonic oscillator ground states. So when you go to the higher lambda levels, you change the form factor, and that would actually induce some effective attractive interaction, even if your Baire interaction is purely positive. So that's a more specific answer to your question. Okay, so the exact soluble model that I proposed in this work actually also has a Gaussian interaction. Why is the Gaussian interaction useful or nice? Because the Fourier transform of a Gaussian is also a Gaussian. Here, I assume the interaction is actually isotropic. So I have an isotropic Gaussian. But when I combine this isotropic Gaussian with an anisotropic Gaussian, I get another Gaussian, but with a reduced anisotropy, because I'm mixing up something that's isotropic with anisotropy. And I can immediately read out the anisotropy exactly. And because it's a mixture of isotropic Gaussian with anisotropic Gaussian, the result of the Gaussian is always less anisotropic than the original Gaussian. So qualitatively, it immediately tells you that the composite fermion problem should have less anisotropy than the Baire electron, which only knows about the effective mass. Okay. The other observation is at this point, I have not even told you what's the fitting factor, because this is a general statement about the Hamiltonian. Now, this property applies to any fitting factor, 1/3 and 1/2. At 1/3, at least within this model, you should therefore have exactly the same anisotropy as 1/2 problem. So as a result, at least within this model, the measured anisotropy of the composite fermion Fermi surface should be exactly the same as the anisotropy in the measurement that has been done at Princeton. Okay, so this prediction agrees quantitatively with experiments and has been confirmed quantitatively in numerical work. Let me actually, in the interest of saving time, don't get into the details. Turns out it also has a very good way to actually connect quantitatively to the more detailed later measurements, which actually finds that there seems to be a simple relation, which is square root between the electron anisotropy and the composite fermion anisotropy by actually making some judicious choice of the parameters in this exact soluble model. Okay, so now let me actually go to the dynamic aspect. So this I hope have convinced you that this geometrical parameter does exist and can be measured and has been measured, and we have a quantitative understanding of its dependence on, let's say, the electron effective mass. What about its dynamics? So this actually comes to Harsh's earlier question. What's the relation between this graviton that I'm talking about now with the magnetorotor? So it has been argued that, already mentioned, that the quantum dynamics of this metric should actually give rise to a spin 2 excitation called graviton. How is that related to the magnetorotor? that people have been talking about over years. So this magnetoroton is best defined at finite wave vector, at a wave vector that's of order the 1 over the magnetic length. But when you go to long wavelengths, it typically enters the quasi-particle quasi-Hopf continuum. And it's not clear whether you still have a well-defined mode in the long wavelength limit or not. But this new way of thinking about it seems to suggest that you should have a well-defined mode even in the 0 wave vector limit, okay? But the question is, how can you actually probe it, or how can you actually excite it? So obviously, we cannot use a standard, let's say, cyclotron resonance type of measurement, which is basically try to use a single photon to excite it, because there's a mismatch of quantum number. A photon carries angular momentum 1, but this carries angular momentum 2. So if you cannot use electromagnetic wave or photons to excite the gravitons, what can you do? Well, the obvious answer is to use gravitational waves, well, of course, in quotation mark. So we, of course, all know these days we have a gravitational wave propagating through the room. But that was actually not the case when I made this proposal in August of 2015, which was actually a month and a half before the very first LIGO signal. So this actually got me into refuge trouble, because refuge doesn't believe there's such a thing as a gravitational wave. Of course, I'm not really talking about the LIGO gravitational wave. It's actually an analog of gravitational wave, which is actually sound wave. Because the acoustic of sound wave actually induces a string, as Harsha and I were actually just talking about earlier in the morning, that behaves like a gravitational wave. So how do I know that? Well, okay, so I actually skipped the relevant discussion of the experiment. So the way that the experimentalists, one of the ways for the experimentalists to actually induce or change the effective mass is by applying strain, because the strain actually causes a distortion of the crystal that changes the effective mass tensor, which to me is the metric tensor. Now, acoustic wave propagating through the crystal induces local oscillating strain, and therefore it should be inducing an oscillating metric tensor, and that's exactly what gravitational wave does for you. So, well, there are different ways to do this, but I'm mostly going to be focusing on the first one, which is the gravitational wave, actually sound wave, is propagating perpendicular to the electron gas, so that the wave vector is actually 0, because the electron lives in a 2-dimensional plane. So the projection of the wave vector is actually 0, but frequency can be controlled. So I'm not going to go through the details. You can actually work out the way this sound wave of gravitational wave couples to the electron gas. The end result is that there's a D wave coupling. So therefore, it should excite D wave or spin 2 excitations. So, the prediction is that the graviton should actually show up as a fairly sharp resonance peak at the energy of the graviton when you look at the spectral function of the so-called gravitational wave, or experimentally, if you measure the absorption rate, there should be a resonance peak in the graviton energy. So we have done numerical calculations for this essentially linearly polarized gravitational wave, and we indeed found very sharp graviton peaks. However, the original way of doing things does not reveal the chirality of the graviton. So at 2 dimensions, L equal to 2 excitation should come, at least in principle, with 2 possible polarizations, +2 and -2. So in later work, which actually can be tested more directly experimentally, as it turns out, we found that actually the graviton has a single chirality for the laughing state. And that chirality is actually -2. So this is revealed in the spectral function. So you can actually decompose the spectral function, original spectral function, into 2 pieces. One corresponds to +2 excitation, one corresponds to -2 excitation. And we find that for the laughing state, you only have the -2 excitation. And we have a very simple way to actually understand that. But before I get to it, let me just say that this is something that you can probe using polarized Raman scattering. So Raman scattering is different from cyclotron resonance because that's a 2-photon process. You absorb a photon and then you emit a photon at different energy. So 2-photon is like a graviton because 1 + 1 is 2. So this actually predicts that if you use a specific polarization of the incoming photon and measure the specific polarization of outgoing photon, you should actually be able to reveal the chirality. But the existing experiment didn't do that, but at least you get the energetics, and the energetics seems to actually agree reasonably well with the existing experiment. And for the more read state, we also, just like Laughlin state, has -2 polarization, but not +2. Okay, so this was published in this 2019 paper. Well, so let me now explain what's the difference. The difference, of course, is that, yeah, I'm aware of the fact I'm running late. Maybe I can take 3 or 4 minutes, if that's okay. Okay. Yeah, I'm getting to the final punchline now, which hopefully will be relevant for ongoing experiment. So we have this this dancing rule that you cannot have 2 dancers getting close to 3 steps, or there's a minimum relative angular momentum of 3. The Pauli principle, on the other hand, allows a minimum relative angular momentum of 1. So graviton in this picture is that you actually turn a relative angular momentum 3 excitation to a relative angular momentum 1 excitation. And that, of course, changes the angular momentum by -2. So that's why this is -2. But +2 doesn't do anything because the Laughlin state allows any relative angular momentum above 3. But this is not allowed. So therefore, the most naive picture of graviton is actually finding such a pair in the Laughlin. That's a very straightforward way to understand the polarization. But anyway, so finally, the dancing pattern at 5 halves, for which the more read state is actually a candidate, is still unclear experimentally at this stage. And there are other competing states like particle Pfaffian and anti-Pfaffian, et cetera, which I'm not going to discuss in detail now, other than saying that for the anti-Pfaffian, basically you just replace these electrons by holes. Because for half-field lambda level, you have particle symmetry. So you can have a whole state that is doing the same thing, but the holes have the opposite charge. So therefore they have the opposite chirality. And indeed, we find that if you have a purely particle symmetric Hamiltonian, you will find no polarization for these gravitons. But when you perturb it away to favor either Pfaffian or anti-Pfaffian states, they have opposite chiralities. So therefore, by probing the chirality of these gravitons at 5 half, it allows you to hopefully determine the exact nature of the state. So that's my last technical slide. This paper just came out in print about a month ago. So let me actually, since I'm already running late in time, let me just put out my closing remarks, which are mostly propaganda, and stop speaking. And thank you very much.
All right, so we can take some quick questions. Actually, let's start in the back of the room.
So I remember you said you cannot excite this graviton mode using electromagnetic waves.
Yeah, okay, so I need to clarify that. So I think the more precise statement is that you cannot excite the graviton using a single photon.
Okay.
So that's a selection rule, forbidden selection, basically. But Raman scattering, of course, is also electromagnetic wave, but it's 2-photon process. So therefore, if you use 2 photons, in the Raman case, it's 1 in, 1 out, you can excite the graviton. Or another idea, which I didn't discuss here, is to actually using nonlinear optics. You try to actually look at the intensity dependence of response to look for the 2-photon absorption process. So that could actually also excite the gravitons.
Okay. So,
yeah.
But would the 2-photon process be suppressed?
No. So when you say the 2 photon, you mean absorbing 2 photons simultaneously.
Yes.
Yeah, that will not be, but nobody has done that. Raman has been done. So yeah, so I'm having my bets on the Raman experiment, which I think is ongoing in Pinlock's group at Columbia right now. Yeah.
I should also say that some people might have to leave for classes and so on. So maybe what we'll do is we'll continue the discussion, but for people who have to leave, let's just wrap up the formal proceedings and thank the speaker. And we can actually give real applause.
Thank you very much.
This is another thing that doesn't work so well on Zoom.
That's right.
Yeah. All right, let's go on to more questions. So I think, Kurt, you have a question?
There are Zoom questions.
Oh, there's Zoom questions.
Oh, okay.
Let's just take Zoom questions then.
Yeah, so what I had a question, you rely on mass anisotropy. Does this imply it is easier to see in whole cases?
Why would that be easier for holes than for electrons? Yeah, okay.
I mean,
I don't see, I mean, from what I have talked about, I really don't see any difference between electrons and holes, other than, of course, the priority is actually reversed. But the effective mass for the electron and the hole should be more or less the same, unless you're talking about different bands.
I think he's talking about different bands.
what do you
okay.
need? Let me clarify my question.
Okay.
I was thinking usually in most semiconductors, the valence band maximum has actually some kind of natural anisotropy, whereas the conduction bands, I mean, there's a whole Conluttinger Hamiltonian for it, right? Whereas the conduction band is usually anisotropic. So isn't it that anisotropic mass that eventually translates into your problem as a...
Yes. Okay, so let me actually say a few things which I think are related, but may or may not address your question directly. So for me, especially for the dynamical aspect, what's important is you can actually control or change the effective mass. So for the experiments that I talked about in some detail, but I guess I skipped most of the details by Mathur, I believe this is actually a, let me see if I can tell from the, so this may actually well be a, this may well be a whole sample as a matter of fact.
Mm-hmm.
Yeah, but what matters here is, in this case, the effective mass is isotropic without the strain, but they are able to change the effective mass and isotropy by applying a strain. So it's a change that matters here.
Okay. Okay, thank you.
Yeah.
There's another question from Zoom.
Okay, great.
So Mandela, you can just unmute yourself.
Oh, can you hear me?
Yeah.
Yes.
Yeah. So yeah, my question was, so is there a relation between this metric you define with the effective mass tensor and this quantum geometric tensor, this Fubini tensor over the quantum states?
Yeah. So Hashi and I were actually just discussing that in the morning, as a matter of fact. So so actually I didn't write down full theory because I didn't actually work on the purely theoretical aspects of it. But let me actually, well, I don't have a reference here, but let me just point out that Song and his collaborators have been working on the theory of these gravitons. So in their theory, there is an internal metric, which is their dynamical degree of freedom, or the field of their field theory. And this, I mean, in my language, the effective mass tensor is a background metric that couples to this internal metric. Now, the internal metric here, well, the physics of the internal metric here is really geometric. This is it's basically this. So this, I don't think, is directly related to the metric of the quantum states. There, of course, you have a parameter-dependent quantum state, like the lattice momentum dependence of the periodic part of the one-year wave function. So I don't think that's the same thing. So here, this is really just the internal correlation. This is really encoding the internal correlation. Mm-hmm. On the other hand, I mean, Hashi and I were just discussing in the morning that you may be actually write down some kind of a gravitation-like theory that actually has this geometric this quantum geometry metric as a fundamental degree of freedom, I think. Yeah, so we're actually going to continue this discussion, as a matter of fact, later in the afternoon.
Yeah, I mean, because like as a follow-up to that question,
yeah.
I was wondering, like when we're describing, first you were talking about topological phenomena, and when we want to describe those in some continuum model, we have like this Chern-Simons term.
Exactly.
So for this gravitational effects, is there like some term you could add to the action?
Yes. So this is actually exactly what Song and his collaborator has been doing. So one thing I think is pretty clear is that the Chern-Simons theory does not capture any of these. So it only captures the topological aspect of it. Now there is actually a gravitational Chern-Simons theory, which actually captures some aspect, not quite this, but some aspect of the physics related to what happens when you put a quantum Hall liquid on the curved space, like sphere, okay? So you can actually write down a Chern-Simons theory, not in terms of the pH field, but actually in terms of the of a metric. But that's yet another aspect, which I'm sure is related. I actually don't have a very deep understanding of it, but still I claim it's different. So this is fundamentally a dynamical theory here, because we're talking about excitations. So and they're not universal. That's the key.
You would need, in addition to the metric, you would need a curvature tensor, right?
Yeah. So you have something that couples to the local curvature of the space in the gravitational Chern-Simons theory. Yeah. But this is yet another different piece, which is I think still work in progress.
So I think in light of the time, I'm going to swing away now and just let Kurt ask the final question, and then we wrap here.
It must be a non-relativistic graviton, right?
Right. So it's certainly not the Einstein equivalent graviton. No. So first of all, it's not gapless. It's actually gap, and the number of polarizations is also different. Yeah. So actually, I mean, again, Kasia and I just talking about. So you must be aware in 2+1D.
Yeah,
there's is actually no graviton because the Einstein gravitational theory is actually topological.
So it's a gapped single chirality.
Exactly. Yeah. So therefore, the name of graviton is in some ways misleading, but I would like to think it as being provocative, and I think that probably.
Well, that is what you get if you take Einstein gravity coupled to the Chern-Simons term.
Is that right?
You get exactly that. Yeah.
I see. I'm not aware of that actually.
Yeah.
Aha. Very interesting. Very interesting. Yeah.
Also, Kurt works on massive gravitons, so he.
Okay. So mass is not a problem.
So yeah, he'll forgive you for having a gap.
Okay. Well, that means the right place. I think it's the right choice to show up here in person.
Yeah. All right. Well, on that note, let's wrap up here, and thank you again very much.
Thank you.